Very good noon all. Today, I'm going to present on Pore solution chemistry of expansive heat cure cementitious systems. Already many research works have been done in understanding expansive nature of cementitious systems. However, a good number of research works have shown not all the systems experiencing TEF will result in expansion. In this presentation, we will see how we can differentiate expansive and non-expansive cementitious systems by studying the pore solution chemistry. For that, first we have to understand the mechanism of delayed etringate formation. Etringate, a normal hydration product precipitates within a day of hydration in normal temperature conditions. However, with the introduction of heat in the seep-cured concretes, the precipitation of hydration is hindered and monosulfate precipitation is favored, leaving a lot of free sulfate ions. At a later stage of hydration, these sulfate ions will react with monosulfate and form etringate back in the systems. Since this precipitation is occurring in a very confined space, it may lead to expansion and cracks, which may affect the durability of concrete. Quantity of etringate precipitating in the confined space may be the deciding factor whether the system will be expansive or not. However, to understand that, we have to wait for months, if not years, to get a system is expansive or not. So, if we can understand this in a few months of time, it will be very, very beneficial. So to understand this, we think studying early age pore solution chemistry of cementitious systems will be helpful. To do this, we chosen an Australian general purpose cement with low sulfate and alkali content in it. With the cement, we increased sulfate from 2.3% to 4%, and alkalis from without altering the alkalis in the system. And for the second system and the third system, we have risen the sulfate and alkalis both in the system to 4% and 1% respectively. And with this, we made mortar and cement-based specimens and exposed this to two different heat curing regimes. One at ambient temperature condition for reference purposes, and one at 90 degrees Celsius for 12 hours to generate DEF in the system. After heat curing, the samples are stored in time saturated water for further curing. So we have done some basics DEF tests like linear expansion studies and a microstructure analysis with the help of SEM to understand where the DEF precipitation occurs, track the location, and other characterization studies such as X-ray diffraction and thermal mass loss curves to track the etringate formation in the cementitious system. And finally, pore solution chemistry by extracting the pore solution of hardened cement paste and studying it over a period of time, say starting from 4 hours to 30 days. And the results are, first we will see the linear expansion of cement mortars. Here from the graph, it is evident that ambient cured mortars didn't show any expansion at all, irrespective of the chemistry of cement. And for the low sulfate and low alkali cement mortar, when it is heat cured, also it doesn't show any expansion. For the 4% sulfate alone modified system, we can able to see some level of expansion, but after a year of induction period. And that too, it's not very high expansion at all. And also for the 4% sulfate and 1% alkali mortar, where we can see a very high expansion, and also it happened very quickly within 100 days of induction period. We can able to see the mortar started expansion. Mortar started expanding. So, what makes the difference? Why some heat-cured mortars are expanding? Why others are not expanding? So the answer lies in the chemistry of the cement, and similar results have been achieved by other DEF research works also. for the similar chemistry systems. So to understand whether DF really forms in these systems, we have done some XRD studies where we can see the primary ettringate is stable throughout the irrespective of chemistry of cement. We can see a stable ettringate peak in the ambient cure systems. Whereas in the heat cure systems, at the end of heat curing, we couldn't be able to see any ettringate peak, suggesting the ettringate precipitation is hindered by the heat curing process. To confirm this again, we have done some TGA works where we can see some deep mass loss occurring between 80 degrees Celsius to 100 degrees Celsius in the ambient curing, indicating presence of primary ettringate, whereas it is we are able to see only a shallow depth mass loss occurring in the heat cured cementitious system, indicating the absence of primary ettringate. So upon further curing in lime saturated water, at the end of day 30, we are able to see the ettringate are forming back in the system. However, we cannot tell whether with this results, whether this cementitious system will expand in the future or not, because the peak heights are not very so different to differentiate between different chemistry of cements. The differences are very marginal. And even if we have to go for the quantitative XRD, we have to wait for months and we have to track the XRD pattern for months to, along with the expansion results, to study that. So instead of doing that, what we have done is we studied the chemistry of the Pore solution from 4 hours to 30 days. And we are able to see for the alkalis and the sulfur for the ambient cured cementitious systems, irrespective of chemistry, we couldn't be able to see much of a dissolution differences both in alkalis and sulfur. Whereas for the heat cured systems, we are able to see some differences here. For example, for the 4% sulfate and the 1% alkali expansive mortar, the alkali dissolution is the largest for that. So correspondingly, if we can see the sulfur dissolution, we couldn't able to see much differences in the low sulfate, low alkali mortar when comparing with the mildly expansive 4% sulfate mortar. We couldn't be able to see much of difference in the sulfur dissolution. However, for the system which gave the maximum expansion, which is the 4% sulfate and 1% alkali cement mortar, we are able to see the real difference in the dissolution of sulfur ions, which suggests more the sulfur ions are there in the liquid phase at the end of heat curing, means at the later stage, lot of sulfates are available for the reaction with the monosulfates to precipitate more ettringate to give some ore expansion at the later stage. That's what we can infer from the Pore solution studies. Apart from that, we have done some micrographs with the help of sun, and we can understand when you compare the later age micrographs with the early age sulfur ion concentration, we can understand the correlation here. For example, here the ambient cure specimens where very low sulfur is rotated in the liquid phase did not have any later age ettringate in the micrograph, which is understandable for the ambient cure system, where we expect uniform formation throughout intermixed formation of primary ettringate, where we won't see a cluster, distinctive cluster happening in the because due to TEF. In the case of non-expansive heat cure systems, although there was an increase in the sulfur ion at the 24 hours, at 58 days, no ettringate cluster visible in the micrographs. Voids due to the accelerated hydration alone is visible, but absence of ettringate cluster matches with the non-expansive nature of the system. Here, for the expansive system, which is the 4% sulfate and 1% alkali cement mortar, we can see a cluster of later age ettringate precipitation here in the micrograph, which had high sulfur ion concentration at the end of heat curing, showing the correlation of sulfur ions at the end of heat curing the liquid phase and the later age ettringate precipitation. Thus, from this research work, we can able to conclude with a mere later age precipitation, we cannot judge, we cannot predict whether this particular system will undergo expansion or not. But with the sulfur ion concentration from the Pore solution chemistry, we will be able to see a clear difference between the expansive and the non-expansive cementitious systems. So the more the sulfur ions in the system after heat curing means, there are higher chance of ettringate getting precipitated in the later stage of hydration. And also, some researchers say it's only the Pore solution chemistry is only 10% of the total representation of 10% of the total sulfate ion concentration of cement. But even if it is true, with that 10%, we are able to clearly distinguish between non-expansive systems with the expansive system. That's all. And thank you. We like to thank Holcim Australia for sponsoring these studies, and Indian Institute of Technology, Madras, for allowing me to do the Pore solution studies in their campus. Thank you.